Hello. Imagine a self-service exam form counter in a department. There is no staff involved. There is no queue manager. Students are arriving randomly. Yet somehow, no two students submit the form at the same time. Now, how this is possible? So here, crux is like each student picks a number and waits for his or her turn. Now replace the students with processes. Students would be processes and font submission desk is the critical section. Now problem is if multiple processes wants to enter in the critical section simultaneously, it can lead to race condition. So let us understand the bakery algorithm. Bakery algorithm is meant for n processes. So here each process picks a number, waits until its number is smallest and executes the critical section and lastly leaves. And this ensures fairness and mutual exclusion. Now here we are going to make use of two data structures. One is choosing I, which would be array, where process I would be selecting a number, and number I, another data structure, which is again an array, token number of process I. So let us simulate this process or these processes using function calls right now. So here what we'll do is we'll include header files first. So hash include stdio.h, hash include stdlib.h, correct? Then we will have hash include unistd.h, hash include we don't require now any other file because this is very simple code. So hash define, we'll take n process example. So that's why I'm defining n as 3. So int choosing the data structure that I was referring to and int number. Both of them are having size to be n. Okay, now we have to write the code here. Like first of all, we'll write a code so as to find out the maximum ticket. Fine. So let us write int max integer m equal to 0 for I equal to 0, I less than n, I plus plus. If number of I greater than m, then m is equal to number of I. This is done. So this is for loop and then return m. Okay, now let us write the lock function because process would be holding a lock. So void lock integer I choosing of I equal to 1. Let us initialize this. So number I equal to max, whatever max returns, plus 1. So let us make choosing of I equal to 0. Fine. So for integer j equal to 0, j less than n j plus plus. It is right. Wait if process j is choosing. So we have to wait. So while choosing of j, wait if process is j is choosing. So while second while num number j is not equal to 0 and number j is less than number I, or correct. So this and is for comparing this. Fine. Number of j is equal to number of I. Fine. And and j is less than I. Bracket is meant for this, then this for while. So yes. So we'll write it here. Correct. Curly bracket, curly bracket. Correct. So now this is for lock. Now we have to write for word unlock integer I, number of I equal to 0. This is for unlock code. Now let us simulate the processes. So void process int I, lock of I, printf process %d is in critical section. Bracket. Done. Correct. Then unlock of I. So this is for simulated processes that they would be permitted to enter into critical section. Now we have to write the main function, integer main for integer I equal to 0, I less than n, I plus plus. Choosing of I equal to 0 and number I equal to 0. Then we have to call the process 0. So as we are executing it with the order, so process 0, process 1, process 2. Here I am not using any system call like fork. So we'll simulate next code with a similar mechanism. So return 0, bracket complete. Now if you see, this is a simulation, not the real concurrency. Why? Because there would not be parallel execution, no real race condition. It is just to help you understanding the logic of this bakery algorithm. So here what we are doing, we are choosing the phase. So choosing of I equal to 1. So when I say choosing of I equal to 1, So I am picking a number. So when you say assign number, like for example here, when we wrote this code, okay, above. So here we said choosing of I equal to 1, correct? So that means I am picking my number. Number equal to max plus 1, then choosing I equal to 0. That means I have already chosen it. Process waits if like another process choosing other process smallest number or same number but smaller ID, kind of. Right. So here we are having three processes 0, 1, 2. So order can change depending upon what the things are, how exactly it is working, depending upon the value. Right. So here key properties would be mutual exclusion would be there, no starvation and fairness. But the limitations are this is not the real concurrent execution. So busy waiting still present and only this is meant for only conceptual understanding. So no signal, no logs, no supervisor. So yet the order would be maintained. So let us save and let us try to compile this code. And if there are errors, we'll try to evaluate it. GCC my bakery n processes dash m32. So for I equal to 0, so we have to write integer I equal to 0, I plus plus. Yeah, here. So we're done with it, correct? Now let us execute. Process 0, process 1, process 2. You can execute it. This would be just simulation that they are working with order. So here we haven't used signals, we haven't used locks, either we have used supervisor there, but the perfect order is maintained. So हर किसी का नंबर आएगा बस इंतजार करो and this is perfect fairness system. So bakery algorithm proves something beautiful, that is coordination without communication, fairness without control and order without chaos. So next time when you take a token at a counter, remember you are behaving like a process solving the critical section problem. Fine. So in next session, we'll talk about like exactly how the processes do work for this bakery algorithm using fork and later threads.